everyone please turn on your cameras if possible. Everybody from the online participants, can you please turn on your cameras? Puran Chandra ji, can you please turn on your camera? Ravi Kumar ji, Kiran Bhardwaj, Amit Yadav, Parth Rawal, Vijay Shankar, Ramesh Denge, नरेंद्र 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 आवाज आ रही है?
जी सर आवाज आ रही है जी।
आप लोग तो इधर ऑफलाइन आ जाते हैं।
सर आए तो अभी मैं आ जाता हूँ, थोड़ी देर में आ रहा हूँ। एक्चुअली मैं ट्रैवल कर रहा, फिर आ ही गया था लॉन्ग वाला। थोड़ी देर में पहुंच जाऊंगा, आधे घंटे में।
ऑफलाइन आ जाओ आप लोग तो ना।
ठीक है सर, आ जाता जी।
ठीक। Okay, everyone, we are going to start with the session. Now, the next session for today, that is second, will be taken by Dr. Anil Kumar Singla from Slide Longowal. Dr. Anil Kumar Singla is currently an associate professor at the Department of Mechanical Engineering, Sant Longowal Institute of Engineering Technology, Slide Longowal, Sangrur, India. He obtained his BTech Mechanical Engineering from Thapar University, Patiala, ME Industrial from Thapar University, Patiala, and PhD from Slide Longowal. His major research interest includes wear, slurry and cavitation, erosion, surface engineering, thermal spray and hydrophobic coatings, additive manufacturing, cryogenic treatments, and material processing and characterization. He has published 36 essays and papers in international journals of repute. He also has 8 book chapters to his credit. 3 patents have been published under his name. He has also edited a book titled Nanomaterials in Manufacturing Processes, published by CRC Press, Hilder and Francis Group. He has already guided 22 MTech students and currently supervising 4 PhD scholars. He has associated 2 research projects on force control of a single-axis robotic manipulator system during tool workpiece dynamic interactions and FIST as team member, and organized 4 faculty development programs and 1 national conference. He is acting as a reviewer of many reputed international journals. He is also the coordinator of this particular FDP. So, sir, please welcome and share your valuable thoughts with us.
Thank you, Dr. Anuj. Is it okay? Now this session is on defects in 3D printed components and effects of post-processing thereof. So many session has been held pertaining to theme of this FTP on recent trends in additive manufacturing, and much has been said about additive manufacturing. I will be focusing particularly on from the research point of view, that what are the possible defects that you can encounter when you are working on 3D printed materials. It may be any material, maybe stainless steel, it may be any superalloy, non-ferrous material like titanium or nickel. So there will be possibility of lot of defects which could be present in 3D printed components. I will be discussing commonly appearing defects and then some remedial solutions also, so that whenever you are working on 3D printed components, these defects can be minimized or can be avoided if possible. Now this session will go like this. First, I will introduce a brief introduction to additive manufacturing, then defects in selective laser melted components, under which these defects will be discussed: lack of fusion, gas pore, anisotropy, residual stress concentration, non-equilibrium microstructure, balling, as-built surface roughness, hot tears, and fish scales. These are some of the defects which commonly occur in 3D printed materials. Then processing treatment, heat treatment, hot isostatic pressing, shot pinning, sandblasting. Then particularly one section has been devoted to effect of post-processing on fatigue performance. And then briefly I will introduce wire arc additive manufacturing. Now, what are the other defects which appear in wire arc additive manufactured components? And then what are the challenges in VAM? And then what are the certain conclusion based on this session and future openings? Quickly moving to introduction to additive manufacturing. This is also known as 3D printing and is considered as a major innovation of manufacturing technology in 20th century and has been highly valued by many countries. AM offers significant advantage in saving raw materials and reducing processing cycle, because as earlier also it has been told in some of the session that it is the conventional machining method is the manufacturing method is the subtractive manufacturing, in which we have a billet and we remove certain material as per the drawing of the component, and whatever material we remove, major component of that material goes as wastage. So when we choose for additive manufacturing for the same component, then the major saving will be in the material cost. In particular, it can produce complex shape parts with high accuracy and no longer rely on the cutting tool, fixture, dies, and various complicated processes required by traditional machining. So when we adopt traditional manufacturing method, we need a lot of support system like jigs and fixtures, special type of toolings. Only then you can make the component as per drawing. But when we go for additive manufacturing, then the complex shapes, particularly if you talk about, you can say, a very complex design, which are otherwise very difficult for machining, that can be successfully employed, and those are the components which are the most suitable one for producing those components using AM techniques. And this feature of AM make it very unique and very useful. Therefore, it has received extensive attention in the field of aerospace, biomedicine, energy and chemical industry, micro nano manufacturing, and so on. In biomedical and aerospace, the complex are so if we talk about biomedical implants, in biomedical implants, since these are to be used in the human body, the cost is not the matter because as such, for additive manufacturing, the cost is higher as compared to conventional manufacturing. But still, there are certain components, certain areas where cost is not the prime concern. Cost is the secondary concern. But of course, it is a concern, but it is not the prime concern. So even if there is a higher cost, but the product reliability, product manufacturing possibility is ensured by additive manufacturing process, then definitely industry will go for it. Then this is the basic process workflow of AM techniques. We have come out with a publication in Journal of Manufacturing Process in 2021. In that paper, we have given this basic workflow of AM technique. So there is a digital system, a CAD model. From that CAD model, we all do all the pre-processing. We generate .stl file and then 3D data slicing also that is done. And then at the third stage, the prototype build-up takes place. That means actual manufacturing takes place by adding layer by layer. And then, of course, in additive manufacturing, components always need post-processing. So that post-processing is done where cleaning takes place and post-curing and extra material removal and 3D component. Finally, we have ready with the 3D components, 3D printed components. So these are the 4 steps in basic workflow of AM techniques. And as far as additive manufacturing is concerned, there are basically the ASTM standard that is F2792 that specifies the AM process into 2 broad groups. One is powder bed fusion technique, second is the directed energy deposition. These are the 2 major techniques which are used. And what is the basic difference between these 2 that I will discuss in a couple of slides. PVF has developed rapidly over the past decades. It can fabricate a product with high geometrical accuracy, but the costs are very expensive or costs are on the higher side. Besides, as metal powder is used in PVF, which is harmful to people, it requires additional processing system to control the hazardous powder environment. In addition, the size of the additive component is generally limited in PVF. So what we do in PVF is we have powder bed and we use a laser source to melt that powder bed according to the 3D slicing, according to the CAD model, and then 3D component is generated. But in this process, the vicinity of the complete setup, this becomes very hazardous for the operator. So that special equipment is required to control it so that it should not come out and it can be very harmful for the health. And also second limitation of PVF is that in PVF, you cannot manufacture part of bigger size. There is a limitation on the size of the part. You cannot go beyond that, right? So because of that, it has limited application. But of course, the geometrical accuracy and you can say the printing of the component as per drawing, specifically with narrow tolerance, that is possible only with the PVF. The second is the directed energy deposition. This uses laser, electron beam or electric arc as the heat source to quickly melt metal wire or metal powder, forming molten droplets which accumulate on the substrate layer by layer and finally become additive product. Although there is lower resolution compared to PVF, that means the quality of the product is not that high as we get in PVF, and it requires post machining process also. Otherwise, DED has much higher material deposition rate and is suitable for economic production of large metallic components. So this is This is very useful when we want to have a low cost AM products, and that also at a very faster rate and also bigger size. So this is directly used in those conditions. Now these two are the schematic of the two system. On the this A figure, this is for powder bed diffusion and this is for DED, directed energy deposition. The basic difference is here, if you see, there are two platforms. So there are two platforms. Now this platform travel in this direction and this platform travel in this direction. So we have a powder bed and a source of energy, that is laser source. It melts that powder bed frame by frame, layer by layer, and this keep on moving downward. And from this side, extra powder which is required, that we keep on pouring by movement of this, you can say, second platform. And this recorder blade, this is going to push that powder in this chamber, right? So this way, layer by layer, that product is prepared and manufactured. So this is the basic technology schematic of powder bed fusion. In directed energy deposition, we have a substrate plate. Here also we have a substrate plate, and on which layer by layer manufacturing takes place. Both the things, powder as well as laser source, both are fed externally, right? And then melting takes place, and then deposition of one layer over the other layer takes place. So this is the basic schematic of both the systems and the basic difference in manufacturing techniques. Now, if you see in AM, the most important part is energy density function. Energy density function is given by P oblique. Change के लिए So this is energy density function, and this energy density function is given by EV. This is equal to laser power divided by this is your scan speed, hatch spacing, and layer thickness. All the four things have been shown in this diagram. So what do you mean by scan speed? Scan speed is in this section. At what speed this laser source is scanning the platform. And this is the layer thickness. How much thick layer you are depositing in each surface scan. And then hatch spacing means between two scan, what is the difference between these two? That is your hatch spacing, right? And then what is the power of the laser source? All these four parameters put together in this relation, that will define the energy density function. So it is very necessary that for every material, energy density function should be optimized before commercial production. It is not like this that one type of energy density function will be equally applicable to other material, right? You have to conduct certain trial and experiments before reaching a optimal value of the energy density function. So according to the requirement of defect-free production, optimal setting of aforesaid function value is necessary. Overview of different experimental works conducted in last decades, where numerous parameters value of energy function have been coined for desired fine-tuning based on the foregoing experience and consequent institutions. So this is your different researchers have used different energy density function, right? Scan speed, laser power, hatch spacing, and layer thickness. And if you analyze this data, and if you come to certain graphical conclusion, that you will find that layer thickness optimal value is 30 micrometer. for almost all the materials, layer thickness should be 30 micrometer. That means you have to choose the parameter of AM technique in such a way that layer thickness should not be more than 30 micrometer. And should not less than 30 micrometer. So it is in the range of 30 micrometer. Then head spacing is in the range of 80 to 100. Or you can keep it, if you want to have on the lower side, then between 60 to 100. That means in AM techniques, you will keep head spacing from 60 to 100. Okay. Then scan speed. What is should be the scan speed? Scan speed should be 600 to 1000. Oh, sorry, 600 to 800. 600 to 800 mm per second. This should be your scan speed. At this scan speed, you will get best results. Okay. Then laser power. Laser power is in the range of 151 to 200. 200 watt. So keep it in the range of 180. 180 watt. If you choose these four parameters, if anybody who is interested in doing work in additive manufacturing, you can safely and without any doubt, you can keep these four parameters for your manufacturing. Right? These four parameters are very reliable and it is based on the analysis of the literature. Right? And we have used these four parameters in our own research work and have found that these parameters are very suitable for defect-free production. And in literature, it has been found that if you keep these four parameters in this range, then porosity will be minimum, because porosity is the biggest problem in additively manufactured components. And if there is a porosity, of course, that will lead to poor mechanical properties. Because wherever there is a porosity in the material, there is a large possibility of initiation of crack with them. And that initiation of crack will lead to failure of the components. So it is necessary that porosity should be minimum. So to keep the porosity to the minimum level, if you keep these four parameters at this level, then your product will be almost a dense structure. Porosity will be. So this is, if you compute, then these are I have given it in the red. Layer thickness 30 micrometer, head spacing 61 to 100 micrometer, and then scan speed 600 to 800 mm per second, and laser power 151 to 200 watt. So these parameters, if you choose, you will get very good results. Now let us come to the second part, that is defects in SLM components. First one is lack of fusion. So lack of fusion means it is defined as improper melting and fusion of the newish layer with the preceding one. When there is improper bonding, fusion means improper of new layer with a preceding layer, that lack of fusion. When you manufacture the component and if you do it SEM, then if you encounter this type of problem, so this is lack of fusion. That means new layer is not fused with the previous layer, because it is layer by layer manufacturing. First layer, then second layer, then third layer. Each layer should be fused properly with the previous layer. Only then it will be a sound product. So if that is lack of fusion, means if that fusion is insufficient, then this defect is introduced, which is called LOF, right? And based on geometrical morphology, it has been classified into three categories, which have been previously precisely discussed in the study. I have given below a reference where these defects, lack of fusion, has been discussed at length. Primary reason for formation of LOF is insufficient energy density function, which we have discussed earlier. The author concluded that LOF has maximum influence on the fatigue life, because whenever there is a lack of fusion between layers, then it is a potential source of crack initiation. So other define as found for both build orientation. Figure shows the optimal optical micrograph of the edged cross section of this cross section is taken for titanium 6Al4B, part built vertically at higher scan speed, 710 millimeter per second. It has been observed as shown here that the two layer faces remain separated along the interlayer boundary, aligning LOF defect parallel to them due to inadequate powder layer binding. Both LOF and unmelted particle exist together as shown in figure. Now this round particle is the unmelted particle. Both can exist together, right? And porosity originate from initial powder contaminants and trapped gas bubble and LOF. It initiate different surface and subsurface cracks through stress concentration, which in turn affects the build orientation specific engineering performance, including static and dynamic strength. So this is lack of fusion. Now, when you do research and when you take the SEM graph, and if you found that this kind of SEM graph is coming, you can easily identify that this is lack of fusion. Okay, and then you doing certain tests, and if those tests are coming on the load side, then you can correlate it with these defects, and you can justify your results. Second is the gas pore. Gas pore, there is a usage of high energy repeatedly for melting, rapid solidification and directional heat extraction. Too high energy will lead to origination of gas and trapped pores due to material evaporation. So if you see here, if you use energy density function on the lower side, then lack of fusion. If you use energy density function on the higher side, then there will be evaporation of material and it will lead to gas pore. That means higher energy density function is also not desirable, and lower energy function heat input is also not desirable. So you have to keep it in the optimal range. So this is sometime these gas pore appear like crack-like pores, and sometimes we have round pores. For higher energy range, we have round pore. For lower energy range, we have crack-like gas pore, right? So this ultimately lead to, whenever there is a gas pore, that means it is porosity. You are introducing porosity, right? So that is basically not desirable. Then we have anisotropy. Anisotropy means that directional properties, mechanical properties in all directions. So if a material is isotropic, that means it has same mechanical property in any direction. So you have made a wall like this using VAM, right, or any other technique. So there are three axes: x-axis, y-axis, and z-axis. Z-axis is the build direction. We normally, you must have heard this word earlier also in some of the session. So this is build direction. This blue line is the build direction. The material is built in this section, right? So if you take specimen in this section, that means you cut the specimen like this. That means this specimen is making an angle of 0 degree with the build direction. And if you cut the specimen in the horizontal plane, then this means this is making an angle of 90 degree with the build direction. And if you cut the specimen at an angle of 45 degree, that means this is at an angle of 45 degree. So if you are getting same properties in all the three directions, for the all the three specimens, you are getting the same mechanical properties. That means material is isotropic. But it is not possible in case of AM component. Then that is the inherent part of additive manufacturing, that you will get directional variation of the properties if you take sample in these three directions, in the three direction you will get different values of the mechanical property. So this part is called anisotropic, and this is inbuilt in AM. You cannot avoid it, but you can minimize it, right? And you can take your sample in such a way that that direction which is giving you maximum value, you choose you make your specimen, you make your component from that direction, right? Now, out of these three, if you find, now these are the results. So let us talk about, first of all, tensile strength. Tensile strength, if you see, this symbol is used. So tensile strength, this upper line is for tensile strength. So if you see, at angle of 45 degree, you are getting maximum tensile strength. That means you cut the specimen at an angle of 45 degree. If you cut the specimen at angle of 90 degree, you will get a tensile strength which is lower than the maximum value, but still it is on the higher side. But if you take the specimen along the build direction, tensile strength is on the lowest side. Maximum along the build direction. Right? That means ductility will be maximum along the build direction. So you must have this data with you to do any research work in additive manufacturing. Right? These things are very useful for if you want to work in this field. So what are the anisotropy and how it is going to affect the, these are called quasi-static properties, and how it is going to affect those quasi-static properties. Then the next very important defect is residual stress accumulation. Why residual stress is coming? Right? First, we should understand it. Why residual stress is coming? So internal residual stresses are invariably generated during simultaneous layered scanning due to process-specific temperature gradient phenomena. Right? Whenever you are in the process of adding layer by layer the material, temperature gradient is always introduced, and that temperature gradient is responsible for residual stress accumulation. Successive rapid and cooling. There are two figures, figure A and B, showed the development of stresses in the AM process due to cooling and heating of the new formed layer. Alternate heating and cooling during AM process result in the formation of compressive oblique tensile stresses in the neighboring layer that lead to generation of stress concentration pockets. When a new layer is added, and far above the temperature of the underlying part of the new layer of material will first expand uniformly. This expansion will be restricted by the much cooler underlying part, resulting in the development of compressive stresses in the new layer. If you see B figure, whenever you add a new layer, this is the old layer, this is new layer. When you add new layer temperature will be more than the previous layer. So it will have a tendency to expand. But the previous layer, it is much cooler as compared to new layer. So it will not be expand at that rate. So what will happen, since both are fused together, they will try to put stress on each other. So new layer will try to expand, but the previous layer will retain its shape. Rate of expansion is less. So what will happen? It will generate compressive stresses in the new layer and tensile stresses in the previous layer. Right? And whenever cooling takes place, in the next part of the cycle, cooling takes place. Now the new layer will cool faster as compared to previous layers. Right? And when it cools faster, it will try to shorten, it will try to contract. But the previous layer cooling rate is much lower, and it will try to restrict that contraction. And because of that, it will produce tensile stress in the new layer and compressive stress in the previous layer. So this residual stress accumulation phenomena is such that it will going to add residual stresses inside the AM component, right? And it is happening with every cycle. Okay. So this all we know that whenever there is a residual stress in the AM components, in any, for that matter, in any material, if there is a residual stress inside, it is not desired, right? It is going to reduce the mechanical properties of that component. Even a human body, if you are under stress, you cannot perform properly, right? So this way, this is a not desirable, but this is inherent. Only thing is you can optimize it. Another defect is balling. So small size metallic particle with a diameter of 7.5 micrometer were occasionally observed on the surface. This is called balling effect. The metal parts prepared by SLM suffer from the problem of balling. Laser-induced balling is an important factor that affects the surface quality of the SLM part and the densification of the sample. This adverse effect may result in breaking up the liquid scan track during SLM and produce particle in spherical shape. The balling effect is a complex metallurgical process, comes from non-optimal SLM manufacturing parameter and material properties of the powder. This phenomenon, unbalanced viscosity, may cause homogeneous deposition of subsequent fresh powder layer and even causes delamination due to weak bond between grain and layers. This effect is also caused by floating powder particles in the chamber due to flow of argon during the manufacturing process. This balling effect, this is also not desirable, but this rarely happens, right? And this is going to affect the fatigue performance specifically. Then we have as-built surface roughness. This is also inherent in AM components. Surface roughness. Surface roughness, as we know, that if any component has a rough surface, then when it is put to use in application, that roughness on the surface are the potential source of crack initiations. So roughness is always avoided, right? Surface roughness is always avoided. But in case of AI component, surface roughness is invariably a part, right? With the increase in scanning speed, the melt pool size reduces. If you see this wording and if you see this figure, so this is one pass, this is second pass. If you increase the speed of the torch, the laser source, if you increase the speed of the laser source, what will happen? If you quickly scan it, what will happen? Its lateral expansion will reduce. Its width will reduce. If you go at a slower speed, its width will increase. Right? Now these are the two consecutive, you can say, pass. And when you go slow speed, they will overlap. When you go at a faster speed, they will not overlap. If they don't overlap, then surface roughness will increase. So that means torch speed, scan speed, that should be optimum one. उसको ना हम कम कर सकते हैं ना ज़्यादा कर सकते हैं. If you increase the surface speed, scan speed, then also it will add to the unnecessary cost and there is undesirable overlapping. But if you reduce the scan speed, then there will be no overlapping and lot of surface roughness will be there. That means waviness on the surface, and that is undesirable, right? So that has to be optimized. That's why choosing the AM parameter is very important. You should choose the parameter in such a way that these inherent defects can be reduced. Then we have hot tears. The existence of hot tear in the SLM product is a consequence of existence of stresses and high temperature. The formation of hot tear is a consequence of material response during cooling from elevated temperature. Hot tears can exist in variety of material produced with selective laser melting. The hot tears are more critical at elevated temperature. So from when at elevated temperature cooling takes place, at that time these cracks can appear, which is called hot tears. And if you come across these kind of images in your SEM study, then you can identify that these are the result of hot tears, and you must know its reasoning and then how to correlate it with the properties. Then we have fish scales. Now this is also a inherent feature of AM component. A microstructural discontinuity named as fish scale also exists in SLM product. The same is represented in the figure. So exists due to solute concentration during layer by layer solidification of the powder with the SLM process. So powder is made of certain material. So due to this solute concentration, these effects, this surface morphology will appear, which is named as fish scales. So this is as far as defects. If we're going to summarize it, in case of SLM titanium alloy product, the more prominent defects are LOF, gas pore formation, anisotropy, residual stress accumulation, and balling phenomena. Out of the different as reviewed defects in terms of product performance during application, the one caused by insufficient energy input, insufficient energy density function, LOF balling, as built surface roughness, are found to be more detrimental than those by excessive energy like gas pore and hot tears. If you have insufficient energy input, then the defects introduced are more severe as far as performance is concerned as compared to excessive energy. The SLM process parameters such as scan speed and laser power, these are the two most important parameters which influence the generation of defects the most. Therefore, the due care should be taken while selecting these two process parameters in order to minimize the defects. Now let us focus on post-processing of AM parts. First is effect of heat treatment. You have manufactured the AM component. Now you come across certain defects. You want to reduce, minimize those defects. Then certain post-processing technique can be adopted so that the defects can be minimized. First is the heat treatment, which is the most common and most preferable, you can say, post-processing technique for minimizing the defects. Most preferable heat treatment technique for residual stress removal, as suggested by several researchers, is annealing. It facilitates to achieve application-specific high ductility. The most prominent, you can say, inherent feature of AM component is that AM components are normally brittle in nature. The microstructure is such, because of rapid cooling and heating, that it is going to have a needle-like structure, martensitic structure. Martensitic structure has poor ductility. But in applications, ductility requirement is there. So there is a unique blend of ductility with high strength, reasonably high strength. So ductility is always required. So to introduce ductility, we use heat treatment as post-processing technique. And this is, annealing is the most specific heat treatment. Whenever you treat a surface with annealing, what will happen? Its ductility will improve, but there will be certain reduction in the strength. Strength is going to reduce. The increase in annealing temperature, though reduces the ultimate tensile strength, but breaking elongation increases, indicating a significant increase in the ductile behavior as shown in the figure. So if you see this blue line, this is as built material having high strength, but ductility is low. But if you see this red line and this green line, this is corresponding to annealing at 1050 degrees Celsius, and this green line is a hot isostatic process. So we will discuss it later on at detail. So in case of titanium alloy, this happens due to increase in the beta phase. Alpha and beta, these are the two phases in titanium alloy. So when we increase the beta phase, ductility improves. Now this is its XRD pattern, which also endorse this effect that when you increase the timing of the annealing as well as temperature, so the most suitable range they have identified as between 550 degree to 750 degree. If in this range you carry out the annealing for extended period, then the ductility will improve to a great extent. Now this is the various heat treatment temperature which has been used by different researchers, and it has been found that this range from 600 to 750 degrees Celsius, this is giving you the best results for post processing. That means whenever you manufacture a product using AM techniques, you do post processing heat treatment, but in this range from 600 to 750 degrees Celsius. This may vary little bit for different materials, but this is for titanium. From 600 to 750 degree for 2 hours, this is giving you best results. Okay. Next is the effect of hot isostatic pressing. Hot isostatic pressing is, along with heat treatment, you also apply a high pressure. This is called hot isostatic pressing. So this is at high temperature, at a temperature of roughly 920 degrees Celsius, you apply a pressure of 1000 bar for 2 hours in the protective atmosphere, that means in the protective environment, so that no oxidation should take place. Because in case of titanium alloy and nickel alloy specifically, there is a possibility of oxidation. So to avoid those oxidation, we use protective environment. But if you give this HIP processing at 920 degrees Celsius at 1000 bar for 2 hours, then it has significantly good results as far as defects are concerned. These defects are reduction in porosity, which is a dangerous thing, and a reduction in residue stresses, which is quite desirable, slight increase in beta phase, slight reduction in strength, but ductility improves. So all these 5 things, this is for titanium alloy, these are desirable. So HIP is the most desirable post-processing technique which can be adopted by a researcher for improving the performance of the AM titanium 6Al4B alloy, and for that matter for other titanium alloy also. So this is a graph, and this is the SEM image which endorse that why the ductility improves. Now this is after heating, and this is for as built. If you see the morphology of the surface, it is from the surface it is clear that this is the ductile material as compared to this material, right? So because of that, you can say that heat treatment specifically leads to increase in ductility. Here also, if you see, this is as built sample, right? UTS, yield strength and elongation, and this is for HIP, and this is for heat treatment at 920 degrees Celsius, and this is heat treatment for 850 to 550 degrees Celsius. Maximum ductility you can achieve with HIP treatment, right? This is another this thing that HIP stress relieving treatment, and as built. AB stands for as built, SR stands for stress relieving, that means heat treatment, and HIP means HIP. For all the three types of specimen, horizontal, vertical, and diagonal. Right? So this is the one of the research work which has identified, and it has been found that HIP is giving the best results. Then effect of short pinning. This is another post-processing technique. Short pinning is a cold working procedure which causes transverse expansion by plastically compressing mostly ductile material normal to the surface. Short pinning introduces favorable fatigue life increase to the component through compressive stress induction. If your material has compressive stresses, residual stresses are compressive in nature, then your material will have longer fatigue life. Fatigue performance will be high. And if the material component has tensile stresses as residual stresses, then it is going to fail early. That means fatigue life will reduce. With short pinning, we are externally, deliberately introducing compressive stresses into the materials. Right? And that is nothing but it is going to increase the fatigue life of the material. Now this post-processing technique will be used only in that AM component which are subjected to dynamic loading or cyclical loading. If the material is not subjected to cyclical loading, then short pinning is not recommended. Right? So because of this treatment, compressive residual stress and work hardening prevent crack propagation in surface layer, though fails to affect the subsurface crack initiation. It is only a surface treatment. It is not going to affect the bulk core of the material, right? Also, the shape of porosity on outermost layer changes rather than pore volume, right? Thus appear as less effective for very long fatigue lifetime. In another study, it was found that it is detrimental to fatigue performance, decreasing the free fatigue limit by 15% in comparison with the polished sample, which is due to crack initiation from the internal pores. So it's a certainty that it is definitely going to improve the high cycle fatigue strength is not sure. Okay. So that means this treatment alone cannot be used as a post-processing technique. Then effect of sandblasting. Sandblasting, as name suggests, that a high-pressure sand treatment is carried out on the surface. It is just to remove the loosely bonded particles on the component. So after in as-built conditions, this type of surface morphology is there of the material. And when you carry out sandblasting, this is loose particles are removed. Right? The purpose of removing the loose particle is that this should not be act as a source for crack initiation. That means this act as you can say discontinuity. Those surface discontinuities are removed. So other post-processing technique, miscellaneous techniques are abrasive flow machining. This is used sometimes. Laser shock pinning. This is another technique which is used as the post-processing technique. Then friction stir processing, which is now used along with additively manufactured component. We have seen that friction FSP in the conventional manufacturing component, but in AM also it is used to, and it has led to it has helps in grain refinement, reduces porosity, improve micro hardness, and reduces residue stresses on the as-built AM component. In our institute, we have recently purchased FSP setup, and soon some of the students will be working on this, right? वैन का तो अभी हमने दिखाया नहीं ना इनको, वो शायद से दिखाया, एक बार लैब में दिखाया। अच्छा। Now this is effect of post processing on fatigue performance. So if you see this green line, this is basically SN curve for high cycle fatigue. Here we have stress level, that how much stress you are putting on the component. Here, number of cycle to failure. So if you see this line, this is corresponding to hip treatment, right? So if you compare this with as built is this line. So there is a big gap. That means after hip treatment, the as built sample now at a cycle rate of 10⁶, this much strength level, this much stress level they can withstand. So here approximately stress level is below 350, but corresponding to this it is approximately 750, right? So that means strength has improved. High cycle fatigue strength has improved from 350 to 770, 400 megapascal, right? So this is the difference to post-processing technique can introduce. This has been highlighted in one of the research studies. Similarly, this is compared with other short peened electropolished, tribo-finished, as-built and hip. All these have been compared, and it has been found that the short pinning and hip in high cycle fatigue strength, high cycle matlab very high cycle fatigue strength, that means more than 10⁸ cycles. Hip is the most desirable, right? Now this is when you supplement your testing results with characterization, with SEM study, then why improvement in the fatigue strength? So this is the reason of the improvement in the fatigue strength. And you totally 130. 130? No, 130. Now if you see, now this is your martensitic structure, middle-like structure. As built AM component have this SEM morphology, surface morphology. Microstructure will be like this. Now these needle-like structure, they have high strength, but they will reduce ductility. This is called martensitic structure, alpha dash. When you carry out post-processing heat treatment or hip, then the structure will change like this. These laminas will be thickened. There will be thick laminas. These thick lamina will, due to formation of beta phase, and because of that, its ductility will increase. But at the same time, the strength of the material is going to reduce a little bit, right? This is again same 3D this thing. Again, in this study, it has been found that if you carry out hip and you supplement it with chemical etching, hip followed by chemical etching, then it even gives better results as compared to hip treatment alone. Right? So this way, hip plus chemical etching, these can be used for improvement in the fatigue properties or the dynamic properties. Now these are the, if you give a summary of all the effect of the post-processing techniques. Now let us discuss something about VAN. Now why we go for VAN? There are the raw material used in case of additive manufacturing is of two types. Either you use powder or you use wire. Okay. In case of powder and wire, there is a cost reduction. The cost of metal wire is only 1/3 or half of the metal powder with the same material. अगर आप वायर यूज करोगे तो उसकी कॉस्ट जो है 1/3 हो जाएगी या हाफ हो जाएगी. And if you change the source also, you use arc power instead of laser power, then the cost will be reduced by 90%. Further cost is reduced. So wire arc additive manufacturing, one is you are using wire, second is you are using arc power. Both of these factors are going to reduce the cost by 90%. Because of that, this van is now getting attention of the industry. Because the main thing is how to reduce the cost of the AM components. Although there are certain drawbacks with van as compared to other techniques, but still this can be taken care of with suitable post-processing technique, and at least you are able to manufacture a complex symmetry with AM techniques, and you are able to do it. So that is feasible. Now this is one of the study that approximate cost per kg in wire and powder form. In case of wire for titanium alloy, cost is 10,500 rupees per kg. For powder, it is 25,000. So this is the difference. Now this is and I have a video. This has been in the you can say unprotected environment, but we have designed certain chamber also. Students are working on this and they are using it. So this is the detail of the setup. Now let us focus on defects. What are the defects which are encountered in van? It has been summarized in the form of table. First is the crack. So crack is the most severe occur in bimetal. Instead of one wire, you can have two wires also. So that will produce a product made of two materials. इसको हम बोलते हैं, this is in research it is called functionally graded material. Now this is the hot topic these days for research. Functionally graded materials. That means instead of having one material, you are using wire of two materials and you are manufacturing that product. So which is called bimetal. So crack is the most severe in case of bimetal. Similarly, surface finish is severe, that means poor in case of steel. And deformation is poor in case of maximum in case of bimetal. Porosity is maximum in case of aluminium. And residue stresses is maximum in bimetal. And delamination is also high in nickel, and oxidation is maximum in titanium. So these are the cracks, and this is how they appear in different materials. This is some of the study which has been summarized. So if you have proper background with what kind of defects could be possible and what type of material you are using, then probably you can take some protective, because usko research में भी when you are manufacturing certain part, it involve cost. So instead of reducing that cost, you must have a background with you. So these are some of the key issues, challenges. Heat input. High heat input during process result in severe thermal damages to the previously deposited layers. Grain refinement. This is one of the challenge in the microstructure, with the reduction in the heat input has been reported in a research study. The microstructure revealed columnar crystal with large dendrite arms space at a heat input of 2.1 kJ per mm. The reduction in heat input to 0.7 disclosed homogeneous microstructure all over the deposit with the fine grain crystal. That means heat input should be on the lower side if you want to have a better microstructure. Low heat input in VAM process showed a large number of small size pores as compared to medium and large size pores. Then we have, it has been observed that effective wall width was increased with a decrease in torch speed and increase in the wire feed rate. Torch speed को आपने reduce करना है and the wire feed rate that has to be increased. Torch speed and wire feed rate, both speed should be optimized to have a better microstructure. Heat accumulation become more serious with the deposition of successive layer, and effects can be minimized by introducing, this is very important, introducing interlayer dwell time, which is equal to time to reach at a fixed interpass temperature. You make one layer, then you give a pause for certain time. For how much time you should give a pause, that depends from material to material. So by hit and trial, you will come to know that if you are manufacturing so and so material, you should give this much of dwell time. उसको एक pause देना है कुछ time के लिए, then you will put a second layer. Second is the stress and distortion control. Stress and distortion due to residual stresses, which is also a very important issue in case of VAM. Residual stresses result in a reduction of structural stability, corrosion resistance, and fatigue strength. Distortion severely damage the dimensional accuracy. The distortion also hamper the productivity because of the requirement of machining for post corrections. During deposition process, the material expands due to heat addition and a compressive plastic deformation is subjected. So one of the solution for distortion control is high pressure rolling. As you make a layer side by side, you give a rolling process. This rolling process helps in controlling the distortion. If you adopt this technique, then residue stresses as well as structural integrity can be achieved. Then we have surface quality. Poor surface quality of the VAM product is also a concern, a big challenge. Secondary machining process is always required to improve the surface quality. So some of the researchers have used milling operation on VAMmed component to improve the surface quality. Okay? Then milling operation can be used. Another option is you can preheat the substrate to a suitable temperature. You have a substrate plate on which you are building the wall. So that substrate plate can be preheated, right, to improve the surface quality. And secondly, third option is you can use protective environment so that in case of those non-ferrous alloy where oxidation is the biggest concern, like titanium. Corrosion is also another issue for VAM component. So to avoid this, the horizontal plane observe more cooling rate as compared to vertical plane. So there are difference in microstructure in terms of grain size, phase structure, and orientation. This non-uniform microstructure leads to anisotropic corrosion behavior of VAMmed component. So this if you take proper care of the, you can say, your process of manufacturing through VAM, the torch speed, the scan speed, the wire feed rate, then you can control the various, the microstructure of the material. And if you are able to control the microstructure, the associated mechanical properties are bound to improve, right? So only thing is you should, through trial experiment, first of all establish these parameters and then you should manufacture it. Now these are some of the conclusion and future opening for VAM. Most of the research work is carried out on aluminium, steel, titanium and nickel based alloy. Little importance is given to fabrication of bimetal or functionally graded materials. So if you want to work, you work in the functionally graded materials. the possibility of fabrication of functionally graded improvement in the fabrication of bimetal needs to be done. It is observed that a few research is done on online inspection of the bead geometry and defects during the VAM fabrication. The offline inspection of faulty components after the manufacturing lead to higher material loss and higher associated cost. This highlights the need for real-time defect detection, closed-loop control system to reduce the overall processing time and to make the VAM a more robust and potent method. In future, artificial intelligence has a great potential in VAM to improve the product quality and performance. If a new structure is to be deposited using machine learning with sufficient data training from gathered database can provide optimal operating condition for the VAM process. Although AI has rarely been used in VAM right now, it is of great significant potential from the VAM field. AI can be used very successfully in VAM, but no work has been done so far. Right? So these are some of the future opening. Then this is for in general SM. I have already summarized it. So with this, I complete my talk. Yes.
So on slide number 44. So just as bimetals are affecting very enormously. तो फिर हम इसको प्रोड्यूस करने के लिए कौन सा मेटल जनरली प्रेफर कर सकते हैं या फिर वैम पे ही किया भी जा सकता है किस टाइप से कुछ स्टेप्स वगैरह
A bimetal, actually, first of all, we have to see that what is our requirement, what is our application. Accordingly, you will choose two materials for producing a bimetal component. Bimetal means it is a combination of two materials, two alloying material materials, right? If you want to add a particular material to a alloying element, that can also be a bimetal. That means titanium. If you are manufacturing a titanium alloy, titanium 6A and 4B, you want to introduce whatever its negative feature, you want to overcome that negative feature of titanium, you want to add a new material to it. So that can be done. So that can be, that means you take the wire of another material and then you do it. But how these defects will appear, it is a matter of study. Over not much of the work is done in bimetal and functionally graded materials. तो जब तक उसके ऊपर कोई लिटरेचर में स्टडीज नहीं आएंगी तब तक हम उस पर्टिकुलर मटेरियल के बारे में नहीं कह सकते।
तो सर जैसे उस पे स्टडीज करने के लिए तो वही हिट एंड ट्रायल बेसिकली मतलब यूज किया जा सकता है जैसे जब तक कोई
आपकी अगर फ्रॉम द स्टडी फ्रॉम द नॉलेज ऑफ द कन्वेंशनल मटेरियल इफ यू हैव सम डेटा related to that, if you want to add this material to the other material, that what are the possible improvement, anticipated improvement in the properties. If you have that data, then you can go for it. If you don't have any data related to this, you randomly select any two material and try to build a bimetal, then that is not the good approach.
Cost time and
yes, because we don't have study. Either you should have a anticipated, because whenever you do some research work, you have some objectives. What are those objectives? That should be clearly defined. And then you go for it. And objective should be based on certain knowledge, certain data.
We can also combine some AI products to get some brief idea about the properties. Just like simulation.
AI is basically, artificial intelligence is basically based on a database. Whenever you have a database for a particular phenomena, particular application, then AI can help. Because you will tell the module that this is the database which you can take help while giving a decision. So AI हमें वो decision देती है. जैसे during my talk, I was telling that you must give a hit and trial experiment, so then you optimize the parameters. But AI can help to avoid those hit and trial experiments. It can directly give you certain data. Just like I am giving you a data that layer thickness should be 30 micrometer. It is based on certain data, right? So AI, instead of I am telling you, AI can tell us that okay, for you can keep this layer thickness as 30 micron. Laser power as 150 to 200. AI can also give. When we study the literature, that phase can be avoided if you have AI module incorporated into the system.
So that we already discussed about layer thickness, adjust spacing, scan speed or laser power, and optimized rate is provided as per the literature. Then we can use this as a base parameter for bimetals.
Yes, this can be used. This can be used, and then for little trial and experiment, you can optimize.
Sir, finite element analysis is possible for computation of average strength for AM products. Is that possible? FEA.
Fine, I understand, but you can always do FEA. It is irrespective of the manufacturing technique. Whether you have brought it is
No, for
FEA.
average strength computation, we do post processing on AM products every time. But it doesn't mean that stress concentration can be prevented. Well, whereas our weaker part is formed, so stress concentration increases. So to avoid that one, we usually do FEA for average strength computation. So is that possible in case of the AM product?
Yes, why not?
If there is any significance in the literature, I think see.
Although I have not explored FEA, but it can be done. Whether it is manufactured, first I need to say I got your idea.
So many defects are there, porosity is there.
Yes, you first manufacture the product, then before post-processing you carry out FEA. Then if you found that there are sufficient defects which are coming in the FEA analysis.
No, but in the literature it is not available.
No. Any other query?
No.
From online. Any other query from the online participants? If you have, please raise your hand or unmute yourself and ask the question. Okay, sir. Thank you very much for a very informative and talk about the different, you can say, defects and process parameters that are important aspects for manufacturing a component using a 3D printing. Thank you very much, sir, for sharing your thoughts. Now we'll have a lunch break, and our last lecture for today will be given by the industrial expert, Dr. Sanjeev Katoj. It will be starting at 2:30, so please be on time. Thank you. See you at time.